So we're looking now at section 7.3 that is talking about composite variables. So composite variables is referring to values that are made up of parts. And the very first example, the opposite of that would be atomic. So it's just an atom, it's a single piece. Composite variables are made up of multiple parts. And the first example is an array. And to motivate this, imagine that I wanted you to write a program that would read maybe 10 items, read 10 numbers, and print them out, maybe in reverse. And you got to think about how you would do this. You'd need 10 variables, and you'd need to have a whole bunch of a big program that reads into the first one, the second one, and the third one. But I think you could do that. What if I told you to read in n numbers for some number n, and first you have to ask the user what n is. So first you read in some number n, then you read in n numbers, and you print them in reverse. Now it's a little bit difficult because I don't know ahead of time how much memory, how many variables to use. And the kind of solution that we use for this is something called an array. When we were learning about the PEP8 machine, we saw that it had a whole bunch of memory with 8 bits per value, and each value had an address going down like that. And if I wanted to jump into position 6F, I could just fetch the value at that address. This is the same idea as an array. For that to work, you have to have a big collection of values, and each value is the same size. So it's homogeneous. An array is basically any time you have a collection, and suppose I had a collection of numbers. The picture that you can have for yourself is a table, or you can think of a spreadsheet like Microsoft Excel, which should be familiar to you. So you have a table like this, and each row has a different number. You're going to refer to an array using some memory location, so array, and then you measure offsets from that location to indicate where the item is. So the first item in the array would be the item pointed to in your code, so it's at index 0. And the second item in your array is at index 1, 2, 3, 4, 5, and in this case 6. So the idea with an array is every single item that you store is the same size. It's the same number of bits. So if I want to figure out what's in the fifth item is at index 4. What's the fifth item in the array? I just take this array address in memory, and I can just add 5 to it, and then that points right to the or add 4 to it, right? And that points to the item at index 4. Okay. What's tricky about arrays is sometimes there's like a mental barrier of just imagining that you can have a whole chunk of data and randomly access to it. But really think about it as a table, and you have a row index. And what's tricky is that the indexes start at 0. Index is start at 0. So the 5th item is at index 4. The 7th item is at index 6. So you can always imagine if I have an array here of 7 items, the 7th item is past the end of the array. You should never access that. The actual values you have are at indexes 0 through 6. Another word for an array, buffer. And trying to access this would be overflow. And that's an error. That's a security problem, because as we know, when we wrote the assembly program, we might have, so this could be, in your assembly, this would be a block of maybe 7 bytes, right? Or 7 times 2, however big each element is. The next thing after that could be some other piece of data, like maybe a password or something else important. And if I tried to write to a value past the end of the array, I'm changing the wrong data. And that is a security problem. You can actually, by writing to an array, go past the array and actually change the program code. So most runtime environments don't just interpret your code anymore the way that PEP 8 does. There's an extra step in there that makes sure you don't do stupid things like that. But the idea here of an array is that it is all elements that are the same size, and you can think of them as being kept in a column of a spreadsheet, and you have the row numbers starting at 0. The position in the array is called its index. Generally we use the variable I to indicate an index. So yeah, I mean, if you wanted to imagine a piece of code that does what I said, read n numbers and print them in reverse, let's just try to think about how we do that in pseudocode, although your book presents this pretty quickly. Actually, let's see what your book has. Yeah, it talks about searching through arrays, but first let's start with how you might read in an array of values. So one thing is, in our pseudocode, how are we going to indicate that there is an array of numbers? So generally what you do is, since everything in the array has to be the same size, we have a concept that we haven't dealt with yet, which is the type of a value. So we've seen that at the end of the day, everything in memory is represented by bytes with bits, right? But how you interpret that data depends on what you mean for it to be. So for instance, if it's a character, then it's only 1 byte for a given character. And then you're going to interpret it using kind of the ASCII table, right? So there's a whole way of interpreting that. If it is an integer, a positive integer, then we're probably going to use 2 bytes on this system. That gives you values from 0 to 365k, something like that. So it gives you a big range of numbers, 0, 0, 0, 0 to F, 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 right? And you're just going to interpret them as binary. And it could be a regular integer, plus or minus, in which case it's still 2 bytes. But you're going to have to represent it differently because the range might be from negative 7FFF to positive maybe 7FFF, because the leftmost bit would be indicate whether it's a negative or a positive number, for instance, right? So there's two different aspects, at least, associated with the type. I'm not ready to go into too much detail. One of them is how much memory each item of data takes up, if it's a character or an integer, or later we'll learn about records. And the other is how you interpret it, or how you manipulate it. So knowing the type tells us the size of an item, especially when we have an array of them. And so in pseudocode, if I'm going to have an array of 10 items, then I'm going to want to say something like, you give it the type, so I'm going to say integer, meaning that I want these, or maybe these plus or minus binary integers, and I'll give it a name, numbers. And then this is similar, like normally we say set numbers to 0, just to mean number is a 0. But now we're going to have a whole list of items. So the convention that your author uses is if you want 10 numbers, they use these things which are called square brackets, and they say 10. Which means you have access to numbers 0, 1, 2, 3, up to 10. All right, so you can kind of visually indicate that out here. This is numbers, and this is index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 is out of range. All right, so you can't access 10. You can only access 0 through 9. So you've got all these little spots. Each one of those is 2 bytes, and they're integers. Okay. So this might be the first line of a program that reads in a list of 10 numbers. Okay. In order to actually read them in, you might set a variable index. So index is what we usually use to indicate your position in an array, to 0. So that means that index is currently pointing at that value, index 0, And while you'll recognize this as a count control loop, while index is less than 10, isn't it convenient that index goes from 0 to 9 when we do this? So it'll visit each cell if we do that. We can read the value, and the value that we want to read, we want to store it at that. So we're going to read in numbers, and we use a bracket. So it's important to recognize this is a declaration. This is saying go out and reserve this much memory, right? So this is a declaration. And when we use a square bracket in a declaration, it says indicates the size, indicates the total size, length of the array. And this is not a declaration anymore. Now we're going to read numbers index. And what that means is this is not a declaration, this is access. So the declaration has the type followed by the name and the size. When we're trying to access it, we're just going to use the name, and we're also going to use a square brackets, and inside that square brackets we say how far down the array to look for the value that we're manipulating now. So we're looking at the item at whatever position index is. So this is going to read, and it's going to store the result in that box, in that value. So it's reading in numbers index, and now that we've done that, we can set index to index +1. So you can recognize this and this as just a normal count controlled loop, and what we're doing is this business right here, that whole expression, the name of the array, the square brackets, and the offset into the array, together that's like one variable. Okay? So really what we've done with our array here is a shorthand for saying, give me 10 numbers, and each of them are 2 bytes. Right? 10 values, each of them are 2 bytes. They're uninitialized, right? Now we do our counting loop, we go from 0 to 9, and for each one we set index. If we were to trace how this code works, then maybe we get something like this. We declare numbers 10, so that's out here. Right? So we actually have 0 through 9 different positions that are declared with this line. Right? And we set index to 0, and so where should I put index? I'll put index right here. And that means that index is pointing right here. While index is less than 10, it is, we read numbers index. So imagine that I'm at the keyboard and I'm going to type in the sequence 4, 8, 2, and I'm just going to repeat it. Okay? So we read in the number 4. Number 4 is going to get stored in the numbers array at the offset specified by index, so we would get a 4 there. Okay? Now we set index equal to index +1, and we check that index is less than 10. It is. And now we're going to read in the numbers array at the offset index. So now index is 1, so this is position 1. What we're reading is going to get stored in that position. Does that make sense? So by incrementing index, we change our position in the array. So I read in an 8. We increment index. So index becomes equal to index +1. And that's less than 10. So now we're going to read in numbers 2. So numbers, go down to row 2. We're right here. We're going to read that in, and we get whatever I type, which happened to be a 2. Going through, index becomes index +1. 3 is less than 10. We're going to read in numbers 3 right here. Index equal to index +1. By incrementing index, you can see us moving down the rows of this array. Right? Index, we're at position 4. 4 is less than 10. We read in a number. We're going to read in an 8. Increment the index. Less than 10. Read a number. We read in 2. Increment the index. So you can see how that works. So since index is 6, we're going to be reading into array position 6. And the last thing we read is 2, so the next thing we read is going to be a 4. Right? So, yeah, I mean, I hope that's pretty clear how that works. If we keep going, we're going to go 4, 8, 2, 4, and index gets set to 10, which is not less than 10, so we never touch this no man's land down here, and then this bit of code finishes. So that would be how you read in a list of 10 numbers and store them in an array. And whenever you're dealing with basically a database, you can think of it as a really big array in some ways, right? An image on your computer, you can think of a picture as a really big array. This is a collection of data, and you can do things like it. So once you've read it in, you can do great things like, how many 8s did I read? You can go back and count it. You don't have to ask the user again, right? What's the largest number I read? What's the smallest number I read? Could I rearrange it so all those numbers are in order from least to greatest? Once you've got it stored here, you can begin to come up with algorithms that manipulate that data in interesting ways. So tasks like searching, tell me if there are any 7s in here. And it should say, nope, there's no 7s. And tasks like sorting, which is where you put them in order from least to greatest or greatest to least, are different types of things that you would do with an array. And we just basically say processing or array processing for dealing with this. When you study linear algebra, all matrices and vectors could be implemented as arrays. So hopefully this makes sense. The only tricks are 0-based indexes instead of 1-based indexes, and also worrying about overflow, going past, you don't want to go past the end or before the beginning, because you might accidentally set index to a negative number. And if index is a negative number, then you start accessing stuff off the other end of the array. And since all we're doing with an array is we are adding offsets to a memory location, there's always a risk of going too far. Right?